Alrighty, we're back with one of our review lectures here. We're going to talk briefly about the history of the atom and the scientists that go along with some of the discoveries that were made, some laws that you'll find in chapter 1 of your textbook, and some techniques that we'll be using in the lab. So make sure you pay attention to some of those because you'll be creating and designing some of your own labs this year. So it's good to know some of the information in this lecture. Alright, so it's storming outside my house right now. If you hear a little bit of thunder, don't be scared. Alright, so when we talk about matter, we usually talk about physical properties of matter and chemical properties of matter. Where physical properties of matter just describe the way it looks, the color, the density, the texture of it, whether it's a hydrate or not. Chemical properties relate to the flammability of it, the reactivity of it. So it talks about some of the ways it can react. We also categorize properties as extensive properties versus intensive properties. So extensive properties, the definition of this is that the property does depend on the amount of matter present in the sample. So obviously mass is an extensive property because more mass means there should be more matter. Or more volume means there should be more matter present. Less matter should be less volume, etc. Molarity is one that you may or may not understand how that is an extensive property, but if you remember the definition of molarity is moles of solute per liter of solution. SOLN is solution. Here we know that the moles of solute is kind of telling you how much is in a liter of solution. So you can have more moles in a liter of solution, that's going to be a higher molarity. So definitely know your molarity definition, and it is extensive. Intensive properties, they're kind of a little more inherent. They're things that are just naturally characteristics about that chemical or about that piece of matter, such as odor. Okay, certain things have a certain odor. Conductivity is one where you have salts are usually electrolytic, whereas nonpolar things, fatty things, are going to be non-conductive. So it's just present. It doesn't matter, depend on the amount of matter present or not. Like everything has a specific boiling point, melting point, or freezing point, and we can use that to identify that particular matter because we may know the published boiling point of that compound. Okay, then we have our states of matter. So we can classify things as solid, liquid, or gas. Some of the characteristics of solids that you'll make sure that you want to know are that, the atoms are tightly packed in a regular pattern. We'll talk about cubic centered and face centered and body centered cubic later on this year. It has a fixed volume. It doesn't flow. It's not easily compressible. It has a fixed shape. Liquids and gases are a little bit more similar. They have the ability to flow per se, where the atoms in the compound or in that liquid or gaseous phase can flow past one another, can easily move past one another. Liquids are a little bit compressible, but not really easily compressible. Gases are very compressible because there's so much space between the atoms in a gas. Let's see here. Liquids are loosely packed. Gases are not packed at all. There's no particular arrangement of a gas. There's a little bit of an arrangement to a liquid, not regular arrangement, but they're a little closer together. So the liquids and gases here are a little more similar in properties. Also talking about physical things, we're going to talk about physical phase changes, where if we're going between solid and liquid, we have melting and we have freezing. Okay, so it just depends on which direction we're going. And we're talking about liquid to gas. We've got vaporization, and some of you guys will know that as evaporation and condensation. So those are pretty easy. And then on the next slide, I have a little information about some more physical and chemical changes. So if we're talking about sublimation, that's going to be your phase change going from solid directly to gas. There's no transition of liquid phase at all. Dry ice is a great example of that. There's no liquid phase as it changes to gaseous state. You can see that here where the solid, just simply the molecules just simply separate, and they go in a couple different directions. They separate out, making more space between them. Something dissolving in water per se is also just a physical process. It's a physical change. So you can see here that we have sugar molecules. They're kind of tightly packed together in their solid state. When it's dropped into water, the sugar molecule itself does not change at all. It's just now separated from its neighbor, and it's got water molecules kind of interacting with it in different ways through hydrogen bonding or dipole-dipole interactions. That's just a physical change. There's no chemical changes at all. A chemical change would be combustion, so burning something. Combustion is actually a chemical reaction where you have a hydrocarbon. In this case, we have propane. That's going to be combusted with oxygen, so O2. It's going to make carbon dioxide and water. And we actually have here propane, the atoms here being rearranged into different compounds, such as carbon dioxide and water, meaning there's chemical change because there's chemical rearrangement. Matter is pretty easy to understand in terms of some of the pure substances versus mixtures here. A pure substance is either going to be an element or a compound. You'll find all your elements on your PTOE, your periodic table of elements. Compounds are just two or more elements put together, so we can have polyatomics put together, or just a metal and a non-metal. Mixtures can either be homogeneous or heterogeneous. Homogeneous means it's uniform throughout. You can't tell the difference between what's in the mixture because it's just looks the same top and bottom of the mixture. A heterogeneous mixture will have some sort of phase on top and phase on bottom, meaning that there's two different compounds here that are unable to interact because of some of their chemical properties. So it's heterogeneous because you can see the difference. It's not uniform throughout. This is a little bit more expansive kind of diagram to describe the differences in different categories of matter. So we talked about our pure substances here, chemicals, elements, binary compounds, and polyatomic, polyelemental compounds. That's going to be 3 or more elements in a compound. If you want to take maybe like H2O, water, that's a binary compound, and you want to break it down, you have to break it down with some sort of chemical method. You can't just say, okay, let me grab the hydrogen and grab the oxygen, because this compound is going to be chemically bound. That means you need to break it down via chemical methods. So water electrolysis is a good example. If I electrolyze this, and this is going to be broken down through a chemical process, it's going to make O2 and H2, and that's oxygen and hydrogen, which are both flammable. Over here, you'll see some of the mixtures. You may remember colloids. For example, if you drive and you've ever driven in the fog, fog is a colloid because your headlights are on usually in the fog, and you can see the beams of light going through the fog. Colloids are characteristic with that. It's called the Tyndall effect, where you can actually see the particles suspended in the air or suspended in whatever media you're looking through. This is all earth science stuff, composite materials. Then we have our homogeneous and heterogeneous again. I just want to make sure that you know that when I say solution, I'm talking about a homogeneous mixture. It's the same thing, it's just another term for it. Something else that you'll want to be familiar with are network covalent compounds. Anything with silicon usually is going to be a network covalent solid. Something like a semiconductor or anything in your cell phones, a lot of times we'll be using silicon, and that's going to be probably a network covalent compound. Alloys is another one. Alloys is just a mixture, and it's a mixture with at least one metal. So you can have bronze. Bronze is not an element, but it's a mixture between two metals, actually, copper being one, which is how you get the bronzy kind of copper color to bronze. Something else like cast iron would be iron mixed with carbon. There's some sort of desirable characteristic about both of those elements. We put them together, we make an alloy. If you're wearing jewelry, you're probably wearing an alloy as well. Alright, so here are some of the laws. You should be familiar with these scientists as well. Lavoisier came up with the law of conservation of mass way back in the day. It's pretty easy. Matter is not created nor destroyed. And that's the reason we can write a BCE or a balanced chemical equation is due to the law of conservation of mass. Whatever we have in the reactants is going to be conserved and present in the products, meaning the mass is conserved, the number of atoms is conserved, which is how it gets balanced. But the number of moles of a specific compound may not be conserved. The number of moles of a particular atom will be conserved. So you really have to make sure you know what you're talking about when you talk about the law of conservation of mass. Law of definite composition or definite proportions Just means, this is the translation part I like a little bit better, just means that chemical formulas or specific compound, you cannot change its chemical formula. It is what it is. So if we have water, we have to have 2 H's for every 1 oxygen. Every compound is going to have a different chemical formula. It's got a definite composition if we're talking about a specific compound. That's a little different when we talk about the law of multiple proportions. Dalton is the one who came up with this, and it's kind of playing off the law of definite proportions or definite composition, because we know we can have water, but can we have a different arrangement of an H and a O? Well, yes, we can. We can have 2 H's and 2 O's, which is hydrogen peroxide. So it's just making sure that people know that you can actually have multiple combinations or multiple ratios of element A with element B. Okay, and so here's an example of that with some data. So if I asked you to kind of think about some chemical formulas that could go along with this information, you'd be looking at here, you'd see the mass of oxygen that combines with 1 gram of carbon. So you don't have to convert to moles or anything, you just need to think about the ratios. You can see that when we go from compound 1 to compound 2, this is going to be doubling. This is the oxygen mass doubling. So maybe for this first one, we have 1 C and 1 O, which is carbon monoxide. But when we go down to the second one, we have to have double the amount of O because of the grams differences here, which is going to be carbon dioxide. We'll be using data a lot to derive certain chemical formulas or just to answer a question. Dalton's also important because of his atomic theory. Most of this is still true except for this one part here. Atoms of a given element are always identical. That's incorrect because of the isotopes. We know that isotopes exist, and that means that there's a different number of neutrons between each of the isotopes that exist for a chemical compound. So such as carbon-12, carbon-13, carbon-14. We can keep going, but between each of these carbon atoms, there's a different number of neutrons, meaning they're not identical. So some of this is not true today. We know about atoms not changing, they're just rearranged. We got compounds are forming, or compounds are just combos of different elements, and elements are made of tiny atoms. We'll talk about subatomic particles a little bit tomorrow, but atoms do have protons, neutrons, and electrons within them, and if you really want to get down into the details, we can talk about quarks. This is just kind of a brief history of the atomic structure and models. We're going to talk about Democritus just a little bit. He was kind of the father of science, I guess, today. He was important because he's the first person to think that matter is made of atoms. And then later on, we have Dalton, J.J. Thomson, Rutherford, Bohr, and Chadwick come in. Chadwick was the one who discovered the neutron, was kind of the peacekeeper within the nucleus. And we're going to talk about more in detail about some of these other guys. Alright, so first off we have J.J. Thomson. J.J. Thomson was really important in the cathode ray tube experiments. The cathode ray tube is what's present in some of the big, huge TVs that are about 2 feet wide from way back in the day. So in the cathode ray experiment, he actually identified the electron and discovered the charge to mass ratio of the electron. He didn't know the mass of an electron, which we'll come to a little bit later with Millikan, but he did know that there was a specific ratio of how much it weighed, its mass was, in relation to its charge. So what you see up here is that this is the cathode ray tube, and he's got a gas in here that's energized. He knew the gas contained something of negative charge, but he didn't know what it was. It was some unknown charged particle. So what he did was he kind of caused it to become really excited, and the gas particles came within this magnetic kind of electrical field, and he had the positive pole on top, the negative pole on the bottom. This gas deflected upward, which meant that it was being attracted to the positive probe here. Attracted. And we all know that opposites attract, so that means these had to be negative, meaning there's some negative body within here. Since it was being repelled from the negative one, that also helped with that theory. With this, there were different gases attracted at a different angle, so maybe you had an angle that went really high up, one that kind of stayed straight, one that kind of stayed really straight. So different masses were creating the different deflection patterns. After all this, he pretty much came to the conclusion that there was a negative particle within here, and he called it the electron. This right here is something that you need to know. Maybe just the general number. If I ask for specifics, maybe just know that it's 10 to the 8th coulombs per gram. So a coulomb is just a unit of charge. We'll talk about coulombs a little bit more later. So actually, I'll go ahead and show you Coulomb's law. Coulomb's law is K times charge of one particle, and I'll just say maybe let's just do 1 times the charge of another particle. Those are both Q's right there, divided by the distance that's between those two particles. So for example, if we're talking about like magnesium chloride, magnesium has a 2+ charge and chlorine has a -1 charge. This would be 2+ times 1- giving us 2 or 2-, and divided by the distance that is between them. It just gives us kind of the strength of attraction between two particles. This is something we're going to use a lot. Another term for this, instead of Coulomb's law, it's called electrostatic attraction. And that was relevant in the cathode ray tube experiments. This is also something you need to know. This is called the plum pudding model, where J.J. Thomson thought that the atom looked like this, where we had a plum pudding where the pudding was all positive. This is positive within the blue part and negative on the red parts here. He thought the electrons were dispersed uniformly throughout the atom, and then Rutherford played off of that in the next experiment. Piggybacking off of J.J. Thomson was Millikan. So we all knew the mass to charge ratio, but we didn't actually know the charge or the mass individually. So J.J. Thomson had published that data. Millikan came out with the oil drop experiment, where he atomized some oil droplets, which are here. This is kind of just a general setup of his experiment. He suspended the oil droplets between two metal electrodes, a positive one and a negative one. And since he was atomizing the oil, he knew the density of the oil. He also knew the mass of the oil. So he knew a lot about the oil. Then he also put in an X-ray. He knew the charge of the X-ray. So once he did some analysis of the oil, he realized that it didn't matter what size the particle was or how large it was. There was a specific multiple of some fundamental value that was always present. So you could divide it by 4, you could divide it by 2. You'd come down to some fundamental value that these were a multiple of. And that's going to be the charge of the electron, which then led to the mass of the electron, which is what we have here. So, they worked together on that. Rutherford tested out the plum pudding model. So he used nuclear chemistry with his experiment. He used an alpha particle. An alpha particle has a 2+ charge. It's actually, this is the isotope notation, helium atom with 4 mass, and this is just the nucleus of a helium atom. These are pretty large in comparison to just an atom itself, because it's got a large mass. These alpha particles were considered huge in that he thought it would kind of zoom right through the plum pudding model because there wasn't a whole lot in the way. But what he actually figured out was that there was some deflection that occurred. So this kind of proved that the JJ's plum pudding model was incorrect. So looking here, this is what he thought would occur, and this is what happened. If you look, you'll see that there's deflection patterns coming off something in the center, which led to his conclusion that there was a dense mass in the middle of the atom, which we now know is the nucleus. He knew that there was no deflection all on the top and bottom of this area, meaning that the large majority of the atom was empty space. And the analogy for this is that the nucleus is a pea at the center of a football field, and the electrons are all around the perimeter, like outside of the stadium stands of the football field, and everything in the middle is empty space, because that's what an atom is a lot of empty space. We also know that protons are equal to the number of electrons when we have a neutral atom. And lastly here, we need to know that Rutherford's model is called the nuclear model. All right, lastly, we have Bohr, and Bohr's model is going to kind of jump into quantum mechanics a little bit. We won't talk about that until later this year, but it's more complicated because it gives us a lot more information about how electrons travel, what do they do when they travel, and where do they actually exist in the atom, because we know they exist on the outer rim, but are there spaces in between that they can exist as well? And the answer is yes. They can exist in orbits, and the orbits are going to be also called energy levels, EL here. And if you look here at this atom, we've got our nucleus in the middle, N1, N2, N3, and so on, where N is the principal quantum number. When an electron moves up an energy level, like here, we start off at N2 and we jump up to N3, it takes energy to jump. It doesn't just happen. So when it jumps, it's actually absorbing energy and it's becoming excited. It's in an excited state. We can't see that absorption of energy. However, we can see when an electron is in an outer energy shell or energy level, so such as N3, and it drops down to N1 here. And when it drops down, it's got to release that energy. So when it releases that energy, we may or may not see it as light. The energy is going to be correlated to specific frequency and wavelength, and if that wavelength lies in the visible spectrum, yes, we will see it. If it lies in a region where we can't see, like infrared or X-ray or UV, then we're not going to be able to see it. It just depends on how far the electron is dropping here. The only thing that was kind of weird about this model was that it's only present and not only relevant for hydrogen, which was really unfortunate because it seems pretty cool that we know all this information, but we only know it for hydrogen, so it wasn't very applicable. And lastly here about electrons. Electrons are actually what's determining chemical reactivity. Protons have nothing to do with chemical reactivity. The electrons are on the outer shell, so they're either jumping around, they're either being passed around from atom to atom, they're being shared. So the volume and the number of energy levels is going to also determine the reactivity of a particular atom. Alright, so tools of the trade is just some techniques that we'll need to know. Gravimetric analysis is one that we'll use a lot, and I'll show you some of these pictures and what they mean here. It's an analytical chemistry method, which means you're going to be analyzing a compound. It's based on mass, so you'll be using an analytical balance with gravimetric analysis. This is something we'll do a lot, so this is kind of resembling a titration. We'll do with acids and bases, and we'll do with KSP, which you may remember from honors chemistry. This is using a Buchner funnel where we have a funnel attached to a stopper, and we're going to have it attached to a vacuum so that it pulls the liquid through and it creates a filtrate at the bottom, and we can collect our precipitate at the top, and then we'll maybe see how pure the sample is, and we'll do some more analysis on it to figure out maybe if it's an unknown compound, what it is. And then we, to really make sure we're doing a great job, we might stick it in a desiccator, which there's going to be little particles down here that are water absorbent, and that's going to help get out some of the extra moisture from your compound to figure out if it's a pure sample or not. Other techniques are going to be separation techniques. So if we have a mixture and we want to separate this mixture into two or more products that's making it up, we can do it in a couple different ways. Distillation is one that you'll actually do in organic chemistry. We may or may not do that this year. It's based off of different boiling points. So ethylene may boil at a different temperature than water. So you can separate things based on their boiling points. You can collect off the one that boils first in a method I'll show you in just a second. Crystallization is one that we'll do in our alum lab. If you want to look that up, it's AULM or ALUM, and it's where you actually have you have a mixture of a solid and a liquid, and you want to just attain the solid. That pretty much means you need to kind of dehydrate it and get all the liquid out. But how can you do that without getting the solid that's also dissolved in the liquid through? So I'll teach you how to do that, and we'll make some really big crystals, and then we'll grind them up and see how pure our crystals are. So it's kind of like precipitation, but you can make some really neat looking crystals with this. Chromatography uses a special paper called chromatography paper, and it's based on IMFs. Certain particles, this is intermolecular forces, certain particles are polar, so they'll interact with polar compounds. If they're nonpolar, they won't interact. So the saying like dissolves like is relevant in chromatography. This is just a setup of distillation. What happens here is you have a sample here, and you're heating it up, and as you heat it up, you're collecting it through this distillation kind of tube, and you're cooling it down with water, and as you cool it down, it's going to be dripping down into this flask, this round bottom flask. In the end, the one that boiled first, so it's got the lower boiling point, was being kind of pulled out and then re-condensed into a smaller flask, where then you'll have a separate mixture. You will have separated the mixture. This is just a heat curve. I just want to make sure we all kind of remember this. If you were doing a distillation or some other a technique of separation, you might be looking at a heat curve to see where certain things have phase change or where certain things evaporate. And then we'll look at phase diagrams as well, especially if we're looking at polar versus nonpolar compounds. Just an example. This is the vacuum that we have to use. So this is the Buchner funnel. It's attached to, it's attached to a stopper that's going to create a seal. And then we connect a vacuum to this. So this vacuum is a hand pump vacuum. So you just keep squeezing it, and then in here it's going to create a really low pressure system, making all the liquid that's in our sample be kind of really pulled out of our solid sample to create a dry precipitate up here at the top, which we'll then collect and then analyze for purity. And there's different ways to do this, but we will be using this one. Gas chromatography is one that we don't have the equipment for, but it's good to know. This is used in kind of quality analysis or quality control in other labs. So say you have a medicine, you're in a pharmacology lab, and you need to determine how many of a specific chemical or mineral is in this Tylenol or in a cough drop. You can use gas chromatography to vaporize portions of that and then analyze the materials present. These are the printouts of data that come from a gas chromatography experiment. We actually will learn how to read NMR, if I can write NMR. And that's kind of what this is. Different peaks relate to different compounds present. So we'll actually learn how to read a little bit of that. Last bit here is about mass spectroscopy. We don't have a mass spectrometer because they're very expensive. You can actually analyze many things at once. Usually it's one type of atom and you're analyzing different isotopes. J.J. Thomson is actually credited with creating this because it related to his cathode ray tube with the deflection patterns. We're going to do an exercise on this tomorrow, but I'll just give you the brief of this. We use mass spectrometers when we actually want to determine the average atomic mass. And where do you find the average atomic mass of something? On the PTOE. So how do we get hydrogen is equal to 1.008 grams? It's not we mass that. We actually do an analysis of with mass spectrometers where you send a sample through this side with multiple varieties of isotopes. The isotopes come to a bend here where there's a magnet. And the isotopes that are really light, so they have less neutrons, are going to kind of deflect more this way on the detector because they're lighter and it's going to be pulled more to the front here. The heavier isotopes stay in the back because they're heavy and they're not affected by the magnetic field that much. So as the detector counts the number of times this spot is hit versus this spot is hit, we can get something called relative abundance. And relative abundance is important in determining the average atomic mass, which we'll do a little bit more tomorrow. Okay, so if you're excited about Schrodinger, who we didn't talk about, it's his birthday today, the day I'm videoing, and this was a cute little thing on Google with Schrodinger's cat, and the Washington Post had some neat videos, so learning is great. If you want to watch this, you can, but otherwise, you're done with the intro to history. Have a great day.